Hi, my name is Jeffrey Chang, and today I'll be talking about our paper, Data, Tracing Knowledge Cutoffs in Large Language Models. So what are knowledge cutoffs? Chances are, if you've played around with LLMs or poked around LLM pre-training datasets, you've seen descriptions similar to the ones shown here. Due to the competitive reasons, many LLM providers often opt to withhold their pre-training datasets and instead report a single knowledge cutoff date. But the single report cutoff raises a few questions. For one, if a model is trained on multiple different resources, say Wikipedia, Archive, or PubMed, do all the resources in the model's training data share the same reported cutoff? Secondly, given a resource, is the model's demonstrated knowledge of that resource aligned to the reported cutoff date? The second question is extremely relevant for LLM users who require up-to-date information from their models. One can imagine an LLM user who queries a language model about tax documents, and even though the reported cutoff of the language model is advertised to be 2024, because the model's knowledge of those tax documents is aligned to an earlier date of 2022, the user gets the wrong downstream answer. To answer these questions, we define the notion of an effective cutoff of an LLM with respect to a resource to be the date that best matches the LLM's knowledge of that resource. Equipped with this definition, we're now poised to ask the first central question of our paper. Are there discrepancies between effective and reported cutoffs in large language models? We hypothesize that these discrepancies can exist because the reported cutoffs typically only refer to the most recent version of a resource that the model has seen during training, but may not account for other possible versions. To make a concrete example, if a model is trained on a specific dump of Wikipedia, say from October 2024, one would expect that the articles in that Wikipedia dump to have an effective cutoff of that dump date, October 2024. However, other versions of those exact same Wikipedia documents may be present in the model's training data, accidentally included through other sources such as CommonCrawl. As such, to answer this question, we estimate our effective cutoffs of models by first creating time-spanning datasets and then measuring perplexity across the data, identifying effective cutoffs from these perplexity measurements. Crucially, we note that our method in estimating effective cutoffs does not require access to the model's pre-trained data, although we do later verify our results by looking over the ground truth data. Before talking about our datasets, we first broadly separate the resources seen by LLMs during training into three categories. First, we have what we call updating resources, and these are the resources in which the majority of updates are edits to existing documents. Examples of these resources would be Wikipedia or legal documents. Then we have what we call building resources, and these are the resources in which the majority of updates are additional new documents. Think archive, news sources. And lastly, we have the static resources, which do not receive updates over time and are, as the name suggests, static. We focus our paper mainly on updating and building resources, and we choose two representative resources, Wikipedia and New York Times documents, as our representatives for updating and building resources. However, in this talk, we'll only be going over our results for updating resources and Wikipedia. To construct our actual dataset from Wikipedia, which we call Wikispan, we first collect the 5,000 most edited topics by edit number, and then, over a period from April 2016 to April 2023, we scrape versions of these documents at a monthly granularity, and this results in a total of 5,000 topics times 84 months of total documents in Wikispan. Now, a document in Wikispan is simply a version of a Wikipedia topic T at time m. For each of these documents, we measure the perplexity of the first 512 tokens across all topics and months, and this allows us to generate perplexity curves such as the one shown here. Shown here is the perplexity of the Wikipedia topic Liverpool under a Python model, and each point in this line graph represents the perplexity of a document at that specific date. Given the set of these perplexity curves for each topic, we seek to aggregate them to obtain a single perplexity curve for each model, and we perform this aggregation through a 95% truncated mean within each month. We use a truncated mean rather than a full mean because empirically we found that there were many examples where documents would turn into stub articles for a few months and then revert back, and so we take a truncated mean to remove these outliers. After obtaining our perplexity curves for each model, we perform a 0-1 normalization across the entire time span to convert our perplexities into what we call relative perplexities. We do this normalization because perplexities are usually not comparable between different model families due to differences in model architecture and pre-training data. As such, performing this normalization will allow us to compare our results for different model families because they're normalized to the same scale. Lastly, we identify the effective cutoffs of these models to be the argmin of the relative perplexity curves, shown here by the red line. Now for some results, and first we have the models trained on C4 in addition to other CommonCrawl dumps. The first model we consider is RedPajamas, which in addition to C4 and its CommonCrawl dumps also trains on the direct included dump from March 2023. And we'll take this date to be the reported cutoff date. And these are the results that we obtain. On the x-axis is time, y-axis is relative perplexity, and we see the dotted line in blue marks the reported cutoff from the model. However, the argmin of the perplexity curve that we find is actually much earlier, in mid-2019. And then we consider Llama, which uses the Wikipedia dump from June 2022. And we find that there also exists a large 5-year gap between the effective and reported cutoff. Lastly, we consider Olmo, which uses the Wikipedia dump from March 2023. And there, we see there also exists a discrepancy between the effective and reported cutoffs. However, this trend of discrepancies between effective and reported cutoffs does not hold for all models. When we evaluated models trained exclusively on the pile, which uses the March 2020 Wikipedia dump, we see that there actually exists an agreement between the effective and claimed cutoffs. Shown here is Pythia, which is trained exclusively on the pile. In fact, all other models trained exclusively on the pile, namely GPT-J and GPT-Neo, also show the same agreement between their effective and reported cutoffs. As such, these results bring us to our second central question of our paper, which is, why do there exist discrepancies between effective and reported cutoffs, and why do they only exist for some language models? To answer this question, we conduct a thorough investigation into the pre-training datasets available, and in the process, we index over 4 trillion tokens. Our analysis reveals 2 major reasons for these inconsistencies, the first of which being CommonCrawl misalignments. So many LLMs train on CommonCrawl dumps, and we find in our analysis that a non-trivial amount of data inside each CommonCrawl dump is actually old data. Especially when multiple CommonCrawl dumps are aggregated, as is common practice when training modern LLMs. The aggregated data is thus extremely biased towards earlier dates. We can see this concretely by indexing over the entire RedPajamas training corpus, looking for versions of Wikipedia documents that were evaluated on in Wikispan. We recall that RedPajamas was trained on C4, CommonCrawl dumps, and also the direct Wikipedia dump from March 2023. And so the first versions we find inside RedPajamas training corpus are those Wikipedia versions corresponding to that dump from March 2023. However, these versions of Wikipedia documents constitute less than 20% of the total versions that we actually find in the entire training corpus. Over 80% of the Wikipedia versions that we find are actually older versions included from C4 and CommonCrawl. As such, this distribution does match up with the overlaid relative perplexity curve that we calculate for RedPajamas. And this brings us to our first takeaway, which is that CommonCrawl dumps contain old data that will bias the effective cutoff of these language models. Our second reason between the discrepancies between effective and reported cutoffs are complications in deduplication pipelines. The fact that CommonCrawl dumps contain old data wouldn't be so much of an issue if deduplication pipelines were able to detect and filter out these older versions. In fact, it is common practice to deduplicate pre-training datasets, and we would expect methods and fuzzy deduplication methods such as min-hash and exact deduplication methods such as Bloom filters to remove these different versions and exact copies of Wikipedia documents. However, we empirically find many duplicates in our pre-trained datasets that have undergone deduplication. Shown here are two paragraphs from different documents in the Red Pajamas training corpus, both versions of Wikipedia article Ming Dynasty. And there's no semantic difference between these two documents, and these two documents only differ by citation number. To see the effect of these duplicate documents, we first recall that models trained on the pile saw an agreement between their effective and reported cutoffs. And this agreement was in large part due to the fact that the pile purposely upsamples versions of its Wikipedia documents in its included dump. If we remove these purposely upsampled documents through further deduplication and then train a language model on the deduplicated pile, we would get these results. In blue is the Pythia model trained on the entire pile with its purposely upsampled versions, and we see an agreement between the effective cutoff in mid-2020 with the reported cutoff. However, when we train a language model on the deduplicated pile that removed these upsampled versions, we see the effective cutoff is now much earlier in late 2018, and we see now the discrepancy between effective and reported cutoffs. This brings us to our second takeaway, which is duplicate documents will bias the effective cutoff towards their version date. In conclusion, we find that there do exist discrepancies between effective and reported cutoffs in modern LLMs. Through analysis of the open pre-training datasets available, we identified two main reasons for these discrepancies, namely, CommonCrawl dumps that are often present in LLM pre-training datasets will include older versions of resources, and these older versions and these that are duplicates will not be removed by deduplication pipelines, and thus bias the effective cutoff of these language models towards very earlier dates. In contrast, we see that smaller, older models trained exclusively on the pile saw an agreement between their effective and reported cutoffs. This is due to the fact that the pile actually contains a very small amount of CommonCrawl dumps, actually less than a quarter of one CommonCrawl dump, when the de facto standard now for training language models is to use 5, 10, even 20 CommonCrawl dumps. Secondly, they also purposely 3 times upsample the versions of Wikipedia documents at the reported cutoff date. Ultimately, our research shows that one must take care when dealing with these reported cutoffs from LLM providers. I would like to thank my wonderful collaborators from Johns Hopkins, CLSP, Mark Marone and Ryan Weller, as well as the guidance from our wonderful advisors, Don Laurie, Daniel Kashabi, and Ben Van Dermy. Thank you.